Well, welcome everybody to GeoHug, and I am so excited. We have Andy Tomkins joining us today. So, Andy is a petrologist and geochemist whose research covers a diverse range of geoscience subdisciplines. So, he's a professor of Earth and Planetary Sciences at Monash University, and he's won the Waldemar Lindgren Award in 2008 and the silver medal in 2021 from this SEG. So Andy enjoys applying the principles of metamorphic petrology to building our understanding of economic geology, global geochemical cycles, the evolution of Mars, and the early solar system. And it's going to be brilliant learning from him today on metamorphic fluids and varieties of orogenic mineralization. So thank you so much, Andy, for joining. It's awesome having you here today.
No worries, Jess. It's good to join you. Should be fun.
I'm thrilled we've made it happen. I was really curious what got you into, well, I was going to say earth sciences, but it's like beyond earth now. So yeah,
Yeah.
what got you into all the sciences? Yeah.
Yeah. It started off as economic geology-ish. I guess it started off when I was a little kid. So I was one of the classic pathway into geology of little kid collecting rocks.
Love it.
But my dad encouraged it. He used to
Yeah.
take me out prospecting for gold and gems and stuff like that. And so even when I was doing sort of year 11 and 12 and did a bit of geology in high school, I was wanting to go to university to become a geologist. So
Yeah.
um, yeah, I'm one of those ones.
One of those ones. I love that. It's everyone's always got such a different story though, so it's really cool hearing. But there is a lot, it seems very common that a lot of people do get encouraged by their parents, which is really cool. Seems
Yeah.
yeah, bit of a common thread there, which is awesome. And yeah, I'm curious what some of your favorite things like throughout your career so far has been.
Yeah, not sure. There's been lots of highlights. Um, Maybe so. What are the career pathways? I guess is one way to think about it too. So the first thing I did after undergrad was go and work as an exploration geologist with Rio Tinto.
Yeah,
That I did that for 3 years before coming back to do a PhD, and I found that flavored the way I think quite a lot.
yeah,
It was pretty helpful for sort of understanding how minerals industry GAs think and helps me talk to them, if I want research funding and that sort of thing as well. Um, so that's always been good. But then some highlights, probably a recent highlight was I went down to Antarctica over summer.
oh wow,
Yeah, so just looking for meteorites and that sort of stuff down there. So that's the other stuff, other research side I do apart from economic geology stuff.
wow, that's cool. That's
Yeah,
oh my gosh, that would be such a bucket list for me to get down there. What
yeah, that was
how
number one on my bucket list for ages, and yeah,
yeah, it's
nice stuff.
quite the expedition to get there, I hear.
Yeah, it was a bit of a mission, but
Yeah.
great fun and yeah.
That is,
Awesome.
oh my gosh, that's brilliant. And I do ask every guest to bring along their favorite pet rock, and I'm very curious what you have for us today.
Right. So I've got lots of pet rocks. Like I've got pieces of Mars hanging
Yeah, I
around.
can see a whole bunch in the wall
Yeah,
behind you.
and
Yeah.
back down there. Yeah. Yeah, I've got bits of Mars in here, but this one I brought along is more of a context rock. So that rock there, people should be able to see all the little white grains in there. That's a calc-silicate rock from the Arkarula area, and all those white crystals in there are scapolite, which I'll be talking about today, is a mineral that contains lots of chlorine and sulfate in it. So I'll be talking about that as a source of interesting ligands that can carry metals as I go through today. So that's a bit of context as well.
There you go. I love that. Well, thank you so much again for being here. I really appreciate you taking the time. Yeah, if you want to share your screen and we'll get stuck into it.
So this is a talk I gave as a keynote at Goldschmidt last year, and also at the International Geological Congress in Korea. So some of you may have seen it, and there might be some slight changes, but most people can't attend those sort of conferences. So hopefully it's new to most people who are listening. And maybe if you did see it, you've had time to think about it a little bit, and you can ask some interesting questions as well. So what I'm going to do is start out with kind of what we know. So I have come into this topic as a gold deposit geologist, and I've worked on orogenic gold systems a lot. I did my PhD on a metamorphosed orogenic gold system and that sort of thing. So, geologists have been working on these things for hundreds of years, probably even thousands of years when you think back to where a lot of the original gold came from. And so I'll step through that as a way of starting about talking about what we know about the metamorphic sources of gold. And then I'll get into some more different new ideas about how metamorphic processes can control metal mobilization in some parts of the crust. So anyway, this is talking about the metamorphic model for orogenic gold systems. So this is kind of like the commonly understood um, model for how most orogenic gold deposits form. There are some other ideas about fluids coming from granites and that sort of stuff. But anyway, let's get into it. So the general idea is that in the deeper crust, water is produced by metamorphic dehydration, and sulfur is liberated at the same time as FeS2 is converted to FeS. And that regional metamorphic fluid scavenges gold and then forms ore deposits in the upper part of the crust with fluid focusing and changing chemistry. And so the metamorphic source region might look something like this. You might go from green schist facies rocks with lots of chlorite in them. Chlorite has around about 12% water in its crystal structure. And when it gets metamorphosed into things like an amphibolite or a biotite schist or something like that, that a lot of that water is released. And that's the metamorphic fluid that we talk about that happens during orogenesis. So the idea is that large volumes of rock in the mid to deep crust undergo dehydration like that, and those fluids scavenge a bit of gold and silver and arsenic. So at the same time, at around about the same pressure temperature conditions, pyrite is being converted to pyrrhotite. So this is pyrite here, FeS2, and generally pyrrhotite is these compositions out here. It's essentially FeS with a little bit of sulfur. Um, and so as temperature increases, you might go something like that from the green schist facies towards the amphibolite facies. You'll hit that reaction curve, and you'll keep progressing along that reaction curve until you run out of pyrite, and then you'll head off into the pyrrhotite stabilities field, and you're producing sulfur by that reaction. So that's the sulfur producing thing in mafic rocks or in metasedimentary rocks, that sort of thing. So that's all going on while the water is being produced. And so this quite a long time ago now, Roger Powell and those guys were suggesting that pyrite breakdown would coincide with water production and that would be the source of gold. We since did some sort of more advanced thermodynamic modeling of all that sort of process. And this is kind of like a numerical model of how water is produced in metasedimentary rocks on the right there. And so it's in metasedimentary rocks in peelites. Water is mainly produced in the lower amphibolite facies. And so that, on that diagram there, it's just a pressure temperature diagram with contours of water production as temperature increases. And the pressure there is in kilobars. Yep. So that's what's happening through this lower part here. You can see this CHL on the diagram everywhere through here. Chlorite's progressively breaking down across that lower bit. That's the thing that's producing water. And that at the terminal stability of chlorite there, you don't really get much water production beyond that, except where muscovite breaks down here. And then up there is, that says wet melting up the top there behind Jess. And that's basically beyond that, you can't transmit fluids through the crust because that would cause melting and that would consume the water and that sort of thing. So that was for peelites. This is for mafic rocks, same sort of thing. It's happening at the green schist amphibolite transition by definition. These are just PT diagrams again, basically with contours of water production again, and basically it's all controlled by chlorite is the message. In ultramafic rocks, you can get serpentinites doing the same sort of thing at around about the mid-amphibolite facies. We'll come back to this diagram a little bit later on. It's probably a little bit complex to explain in detail, but basically what's going on in metasedimentary rocks is that you tend to be breaking down pyrite when in carbonation in graphite-bearing rocks or in graphite-free rocks, and so you end up with low oxygen fugacity. In mafic rocks, you tend to be a bit more oxidized, and we'll get into talk about this sort of later on. For the moment, let's not dwell on this too much. We'll come back to this sort of point later. Yep. So what tends to happen is as all that water is being produced, it tends to actually drive the pyrite breakdown to generate, to balance out the carbon, hydrogen, oxygen ratio. So generally that water, if you've got graphite around, that water will react with the carbon to produce CO2. And so if graphite's around, you'll need to maintain the hydrogen oxygen ratio. And so that will help pyrite breakdown. So in graphitic pyritic rocks, this is kind of what's going on. You're producing a little bit of CO2, H2S, when there's water being produced by the metamorphic reactions. this the ppm buffer means pyrite pyrrhotite magnetite buffer. There's no similar mechanism that does that. So in mafic rocks, um, you haven't got quite the same sort of thing going on. So the amount of fluid that's produced, the amount of H2S produced is less. So this is for mafic rocks up here, contours of XH2S, and this is for graphite-bearing pearlites over here. Point is, you can produce a lot more sulfur in pyritic rocks, which is probably not pyritic graphitic rocks, which might not be surprising to people. We're kind of going over this a little bit quickly, so partly because this is kind of stuff we kind of know already a little bit, and we can come back to it if people want to at the end. That's the chloride outline there. Those are just contours of H2S in a closed system. So a closed system is something metamorphic petrologists model just to understand what's going on. We know that geological systems are open systems. And in the source regions in the lower crust, deformation's going on at the same time. And we know that this fluid production weakens rocks. So this is trying to get people to remember some stuff that they might have heard about in the past. You don't need to know what this is about, really. The point here is that fluids weaken rocks. They allow rocks to deform more easily. And so metamorphic fluid liberation probably helps the deformation, and that is going to help drive fluid migration as well. So deformation allows fluids to move through the crust is what I mean there. So fluids and deformation, I won't dwell on this overstep reactions thing, but there's a bit more detail in there if you want to ask about that later on at some point. Sulfur production probably coincides with fluid flow because all this deformation and metamorphism is happening all at the same time. And so not much fluid is being generated beyond the chlorite outline, so over here in the amphibolite facies. So if deformation is removing fluid, you can't really generate much sulfur in the crust beyond that point. You can generate a little bit here where muscovite's breaking down. So that chlorite outline is kind of like a region of high fluid production and higher sulfur solubility. So that region in there is kind of like the sulfur generation window for metasedimentary rocks. These sort of conditions down here, which is sort of lower upper greenschist facies, lower amphibolite facies at sort of mid-crustal conditions, is mid to lower crustal conditions, is kind of the main window of sulfur generation in the crust. And so these are two different geotherms. Basically, hotter geotherms are better because the sulfur content is higher. So that's for metasedimentary rocks. For mafic rocks, same sort of general story. The amount of sulfur that can be produced is a bit less, basically because of the graphite and the way that controls things. And so in a closed system, this little diagram here is trying to represent a closed system. If you've got no deformation going on, you might have a bit of metamorphic water in there. It'll sort of help this pyrite to pyrrhotite reaction going on, but the fluid's not going to get out of the rock. The reaction's not going to go very well. If you have through flowing fluids, that'll tend to drive pyrite breakdown and it'll tend to strip out sulfur through the rock. So in some respects, deformation is going to control that sulfur liberation, sulfur production and sulfur liberation as well. So this, generally, the point is if you've got deformation going on at the same time as greenschist amphibolite, lower amphibolite facies metamorphism, that's the process that's generating the fluid, moving the fluid through the crust and getting the sulfur out of pyrite that's in the same source region. Yeah, so if you've got fluids moving through a rock that has pyrite in it, that can drive sulfur liberation as well. And this is some of the stuff that's been done by the codes guys. This is one of their papers. These are just laser ablation maps of pyrite in sedimentary rocks, and it's basically showing you that the pyrite contains gold and arsenic and a bunch of other things, silver as well, tellurium. So when the pyrite breaks down, it's liberating the gold at the same time as the sulfur is being produced. And so that sulfur is the ligand that'll bind with the gold and carry it further out of the crust. So when they've done analyses of pyrrhotite, they find that they're depleted in things like gold and silver and arsenic and that sort of stuff. So pyrite in metasedimentary rocks is a great source of gold, and pyrite in metamorphosed mafic rocks is also a good source of gold. It's not a good source of arsenic though. So this paper is Thomas et al. 2011. People probably already know about this. Has been established a little while now. So one of the key points is that arsenic probably comes from sedimentary, metasedimentary rocks. It doesn't really come from mafic rocks. So this is kind of pointing to the idea that all these arsenic-rich gold systems are probably getting some of the metals from the metasedimentary sequences below them. People will have seen this diagram before. In normal orogenic gold deposits, we know that they're produced by um, near neutral pH, reduced fluids, low salinity, sulfur-rich fluids, low to moderate CO2. And people would have seen this before. This is neutral pH fluids that are reduced, moderate oxygen fugacity. They're great for carrying gold as a gold hydrosulfide complex. And so other base metals tend to be carried as chloride complexes. And so you end up producing gold-only deposits that don't have much in the way of other metals. Um, so this is kind of like where we think they come from the crust. There might be, this is the fault valve model that people might know about. Normally we get an earthquake on a fault at the base of the brittle ductile transition. That'll rupture through into the upper crust and you'll get transmission of fluids from the metal source region in the lower crust up to, say, Bendigo or whatever in the upper crust. So one of the typical orogenic gold systems. These are kind of the conditions we think about for metamorphic source regions and depths and that sort of stuff. I'll come back to that sort of thing later on. So normal orogenic gold deposits always look like this. No, that's a really extreme example from Beta Hunt gold mine. Gold's normally hosted in quartz veins. You get sometimes extreme enrichment like this that can be quite hard to understand. And sometimes it's often in highly interconnected along fractures like this too, actually, which is interesting. It can also be hosted in arsenopyrite, arsenian pyrite, that sort of stuff. And this is kind of our latest work just in this general area. It's published in Nature Geoscience last year about how earthquakes cause piezoelectric discharge from quartz, which causes gold accumulation. So if you want to know more about that stuff, go have a look there for some of our latest ideas. And now, so that's kind of, I zoomed through metamorphic controls on gold source for normal orogenic gold systems, which is like Western Australia and Bendigo and Victoria and many places around the world. And so when I was working in the minerals industry, I mostly worked up in the Mt Isa Inlier, which is again a green schist amphibolite facies metamorphic belt. And I was thinking to myself, it's so metal rich up there. Why aren't there lots of orogenic gold deposits? Which is a bit weird. This is what the Mt Isa region in Queensland looks like on a sort of very broad scale geological map. This is the eastern succession. And it's arguably, you could say, is one of Australia's, if not the richest, one of the richest metallogenic regions in Australia. Mesoproterozoic. It's a metamorphic belt. Green schist facies up here and upper amphibolite facies down here. It's got all sorts of stuff in it. Iron oxide copper gold, iron sulfide copper gold, uranium rare earth element, molybdenum, cobalt in pyrite, all sorts of stuff in there. There's only really one gold only deposit in there that's been mined effectively, and people can correct me if I'm wrong there, but there's thousands and thousands of copper, gold, cobalt, sometimes prospects in there, hundreds of uranium rare earth element prospects in there. These green dots on this map here, each one of those is a little prospect. And one of the things I want to highlight in there is the Corella Formation and the Doherty Formation. Some people listening might have been up there and know about these things. These are the calc-silicate rocks in the area. They are rich in scapolite. And you can see how regionally abundant they are. They sort of broadly coincide with where all the copper gold deposits are too. And anybody who's worked on those rocks in that area will know that there's copper everywhere up there. It's just crazy. So I'm going to talk about some metamorphic ideas about how these are formed. There are some older ideas about these being related to intrusive systems. And so this is what people have observed when they've looked at some of these iron oxide copper gold deposits in the Eastern Fold Belt in Mt Isa. So the guys up at, Mark Kendrick was up at JCU when he was doing this work, I think, and then down at Melbourne Uni for a while. Now he's up in Queensland. This is some of his earlier work, and they observed lots and lots of different types of fluid inclusions, and here is the main point. Some of these fluid inclusions contain up to 70% salts, so they're super salty. Some of them are CO2 only, some of them are liquid vapor thingamajigs. So there's a whole variety of things in there. They back in the day they were always sort of talking about fluid mixing to explain these sort of things, and I'm going to be talking about phase separation as an alternative way of thinking about these sort of things as we go along today. This is again from Mark's stuff. This is some of the ideas for how these sort of iron oxide copper gold deposits form. So here they're talking about mixing of a brine coming from here with a metamorphic fluid. Here they're talking about an intrusion, releasing fluids, and then brines mixing in again, that sort of stuff. So this is kind of generally what they were talking about for how these things might form. And these sort of ideas are, you know, persist around the world. That might even be the dominant way of thinking about IOCG systems at the moment. One of the things people were talking about back then was this point here. This is kind of what people thought about for metamorphic fluids. They're always low salinity CO2 poor things. This is kind of coming from what we know about orogenic gold systems. The stuff I was talking about before, they're always low salinity, up to 30% CO2. This is our normal metamorphic fluid, and it's not the same as the metamorphic fluids in this region because there's so many calc-silicates there. So I'm going to start going on about how you get really weird metamorphic fluids in this region and how this model isn't right, basically because we didn't understand what metamorphic fluids were like back then. And our understanding of what metamorphic fluids are like in these regions is different now. So this rock that I've got here is, zooming in on it a little bit, is very similar to that rock I was showing you before. That white mineral there in there is scapolite. This is what it looks like. It's a solid solution of these end members. And you can see there's chlorine and sulfate and CO3 in here. Then anybody who's been, this is one of the rocks from Mount Isa, anybody who's been to this area was probably familiar with scapolite. It's all throughout that Corella Formation, Doherty Formation that I showed you the map of just before that, across that whole region. It's quite abundant. And I showed you that rock before from Arkaroola, which is in South Australia. So there's other metamorphic belts like this as well. And I think some of the ISCG bearing belts in South America also contain scapolitic rocks. So, and in China as well. So I went there with Laura Morrissey quite a few years ago now. Did some field work there, collected a whole bunch of rocks from scapolitic sequence from the Corella Formation. We were trying to go across a metamorphic gradient. So this says 560 degrees up here and 630 degrees here. So it's kind of not a really great gradient. But I'll show you some of the rocks we managed to pick up. Lots of scapolite, a lot of calcite in these rocks. That's kind of what they look like in an outcrop. So well folded, well bedded, metamorphic calc-silicates. In thin section and in electron microprobe maps, they look like this. So here's our thin section view here. This is our scapolite, calcite here. And we've got all sorts of stuff in here. So this is a sulfur map down here and a chlorine map. And you can see this scapolite is zone. And as the scapolite crystal grew during progressive metamorphism, this indicates that the fluids became more chlorine rich as metamorphism progressed. This one over here is telling you about the fluctuating sulfate. This is a map of the sulfate distribution in the scapolite. So there's fluctuating sulfur in the scapolite as well. There are sulfides in all of these samples. And so when we've got sulfate coexisting with sulfide, we're on the sulfide redox fence, which is very oxidized. So the metamorphic fluids are buffered by scapolite and the sulfides, and so the fluids are really unusually oxidized compared to normal orogenic belts. Compared to the orogenic gold deposit belts, they're much more oxidized. More stuff. There's no chlorite in these rocks, so they've lost that initial green schist facies metamorphic fluid. What else we got? Oh, yeah, there's no muscovite. So they've already gone through a fair bit of dehydration. What else we got? This is another interesting thing. So the hornblende and biotite also contain chlorine. This is a chlorine map of the scapolites, but there's biotite and hornblende in here that also have chlorine. And so those are two of the minerals that will progressively break down in through the amphibolite facies and release chlorine and equilibrate with the scapolite and control the chemistry of the metamorphic fluids that are being produced as metamorphism progresses. This is a map of chlorine and sulfur, and you can see that they're variable. So there's sort of varying metamorphic conditions here as all this is going on. Um, so one of the interesting things about some of these scapolites, this is a chlorine map of the scapolites over here. So the green ones over here are scapolites. And again, you've got that increase in chlorine in the rims. Um, some of the scapolitic rocks are graphite bearing and the scapolites are sulfur free in that environment. Come back to that in a sec. Um, These are graphite bearing rocks again as well. Another example, you've got um, clinoproxen after biotite hornbrand breakdown. So you're producing metamorphic fluids probably initially at that green schist chlorite breakdown process, but then you're continuing to produce metamorphic fluids by biotite now. Well, breakdown in calc-silicates. They're a little bit different to other rocks. So there's a bit of a more of a continuous metamorphic fluid production in this sort of rock. And then down here we've got some discontinuous red spots down here of high chloride, and I'll come back to that one in a sec too. So here's some Scapolite geochem. So when I've got meionite on the x-axis here, that's talking about this carbonate end member. And then this is the chlorine content of Scapolite here as a function of the carbonate content. And so you can see we've got up to near 3 weight% chlorine in the scapolites. And that is a linear relationship between the carbonate content and the chlorine content. And then there's the opposite linear relationship between the carbonate content and the sulfate content. And you'll notice, so we're talking about three groups of rocks here effectively. This one down here, the gray ones, those are the graphite bearing scapolites. And they're sulfur free basically because the graphite is a really strong reductant and it takes it down way below the stability field of sulfate. And so what that effectively means is your metamorphic sequence of layered basically they're layered sedimentary calc-silicates. Some of them are oxidized and sulfate rich, and some of them are reduced and sulfate free. So there's a heterogeneity in the source region. There's heterogeneity in the chlorine content and the sulfur content. It's quite variable. So just now a bit of theory about how metamorphic fluids work in calc-silicates to get people sort of recognizing how different these systems are. This is kind of like a general overview of how metamorphism works in calc-silicates. Generally, as temperature increases, you go from water-dominated conditions. This is H2O over this side and CO2 over this side. You go from water-dominated conditions at lower temperatures, and as you go across all these reactions, each one of these reactions produces CO2. So these are all producing things like grossular and wollastonite and various other minerals. You don't need to know the details of what it is. The point is that in any calc-silicate, all of the reactions that are producing the various minerals that you find in calc-silicates generate CO2. You end up with high CO2 fluids as metamorphism progresses. You're basically producing CO2. So if you're dealing with a rock that has a bit of salt in it, a bit of chlorine in it, equilibrating with chlorine-rich scapolite, that sort of thing, you might start out, this is kind of like a generalized schematic idea of how it would work as you go from green schist up into upper amphibole phases. You might start out in a single phase fluid situation, generally going through calc-silicate reactions producing CO2. So you'll head off over this way as CO2 is produced. And you'll eventually hit this two-phase field where you have brine, which is this green bit over here, coexisting with CO2, which is this red line here. So these lines here are tie lines. So at these conditions, you'll have this fluid coexisting with this fluid. And over here, you'd have this fluid coexisting with this fluid. So you're generating a CO2-rich fluid at the same time as a really salty fluid. And you can see if this continues to evolve, you'll end up with this situation over here where we can have brine coexisting with CO2, which is this thing over here, coexisting with halite or pure NaCl. And basically, there's an increase in chlorine in the fluids as metamorphism progresses. Now, if you take that pure NaCl end member, this one up here, once we hit this point up here, and you look at what else is in the rock, this is NaCl on these diagrams here. There's also a lot of potassium around and calcium around and magnesium around. And this is what I'm trying to show here is the eutectic in a NaCl, calcium, potassium, Cl system. The point is this would be molten at only 483 degrees. So that's like lower amphibolite facies. Adding magnesium into this, you get a lower eutectic as well. So though if you do get into that salt field through progressive metamorphism, you'll have a liquid salt around. And the point of that is liquid salts are great at dissolving all sorts of stuff. They're great at, they would be dissolving any monazite, that sort of stuff. They're great at mobilizing things around. If we zoom in on one of those scapolite maps I had before, you do get these little spots of really high chlorine around the edges of some of these scapolites. And perhaps they are little bits of salt that have been left produced by that metamorphic process. So that might be an example of that sort of thing. That's kind of a getting out there a little bit of slightly out there idea on what might be happening in metamorphic, some metamorphic rocks, but interesting one to think about. Getting back to more normal stuff, if we're um, what I'm trying to look at here is the effect of having highly saline fluids on other ligands. So this is the amount of salt in a fluid um, at probably unreasonably high temperatures in this example, but it'll similar sort of thing will apply at lower temperatures. The point is, as you add more salt, you'll more effectively dissolve things like calcium sulfate, calcium carbonate, calcium fluoride, and calcium phosphate. So the point is phosphate, fluoride, carbonate, SO4, you're getting more ligands of everything in the fluid when you have more chlorine around. So that means you are much more able to complex with any metal when you have more chlorine around. You'll be able to form complexes with chloride complexes better than everything else as well. High fluorine and phosphate will be generated if you have salty shear zones intersecting granites, for example. Um, so the Mount Isa source region represented by these rocks is kind of like 550 degrees and 630 kilobars, that sort of range, that sort of pressure. And the fluid inclusions in the ore deposits are slightly less than that, so slightly higher in the crust. And so there's lots of shear zones through the crust. There's lots of similar sort of folding through the crust, so that this pulp valve model would apply quite well in this sort of system. It's similar sort of conditions to what we were talking about with the other orogenic gold deposits. So what would happen to a fluid like that, a CO2 rich salty fluid, as it moves up through the crust? Um, one of the interesting things about increasing salinity is it helps with the whole phase separation process. So normally we don't tend to think much about phase separation in orogenic gold systems, but with these systems, we need to sort of think a little bit differently. This is kind of like an example of a solvus that you guys are probably familiar with this, but up at these conditions up here, you have a single fluid, and when you cross a solvus, the idea is that you will separate out two different fluids. One of them will be heading off towards 100% CO2, and the other one will be heading off towards 100% H2O. This curve here is for pure water, and this curve here is for just a little bit of salt added to it. So the point is that adding salt will increase the temperature at which phase separation will occur. It'll occur earlier as the fluid moves up through the crust. This one is for, this is the single phase field, the two phase field over here for the same sort of diagram we showed before, which is that, that one, same diagram. And the point here is we're trying to getting at moving from 5 kilobars to 3 kilobars. The temperature is a little bit cooler. And if you go from the single phase field here in the deeper crust, as you move up to shallower levels in the crust, you end up with that same conditions. This might be our metamorphic source region conditions, moves into the two-phase field. What that means is as you go from a sort of salty CO2-rich fluid in the source, it'll tend to separate out into a CO2-rich fluid and a salty fluid coexisting with each other. Phase separation will be at much deeper level in the crust than typical orogenic fluids that are produced elsewhere, is the point there. One of the other interesting effects of all this is when you produce a fluid that's over here somewhere, you're actually increasing the activity of water a little bit by doing that. And the effect of that is to dissolve silica. So that means you can dissolve silica along your fluid migration pathway. When we look at the actual ore deposits in these areas, we see that they're really porous in the areas that have been mineralized. So the dark gray in this is magnetite, this is diopside, and I think this might be a some K feldspar in there as well. But there's lots of holes in this rock. The silica's been dissolved out of this rock. When you think about a lot of ISCG systems, they're really strongly silica depleted. So that there's probably more than one thing going on there, but it can partly explain that quartz depletion in the rock by that evolving fluid chemistry. A lot of these systems are also fluorine rich, and so fluorine is also good at dissolving silica. Um, yep. Um, so you end up with a more metal rich fluid by that sort of process. So as you go through that phase separation process, you're taking away some of the CO2, and so you'll end up with this brine that's more salt rich and also decreased volume, so it will tend to be more metal rich. And if you're generating this porosity as the fluid's moving up through the crust and going through this phase separation process, it'll tend to create a porous pathway for the fluid and tend to create this longer lived fluid uh, fluid transmission pathway at and above the brittle ductile transition as those fluids are separating out. Yeah, so that the solidity of the H2O phase can increase significantly through that phase separation process. That can get you to that ultrasaline fluids they see in the ore deposits. One of the interesting things is that coexisting CO2-rich fluid does not wet silicates and has a lower density, so it will tend to physically separate out and get left behind or be lost along the fluid migration pathway. Maybe that explains some of the carbonate pods that you see in the Mt Isa region. People who've worked there might be familiar with those. That's why I'm putting that in there. You'll tend to get a volume expansion going on where as all that fluid moves up through the crust, and you might get breccias going forming that way. Other people have talked about that sort of process before. So um, one of the other interesting consequences about these really saline fluids is they're great at driving albite alteration. So this is an example of what the albite alteration looks like in the area. Up here you can see some pink to white calcite. This is actinolite here. This is a carbonate vein cutting through some calc-silicate rocks. This is my foot for scale, and all this white stuff in here, all the creamy colored stuff is the albite alteration that's replacing this rock here. You can see it's infiltrating along the cleavage in the rock here. And so the effect of if you do that albite alteration to a scapolite rich rock, like the one I was showing you at the start, that when Jess was just introducing me, that rock had about 70% scapolite in it. You can imagine if you're replacing all that scapolite with albite, you're basically picking up a lot of chlorine as the fluid moves through the rock. And the other thing is that when you do drive that albite alteration, albite is the sodium end member of plagioclase for those that don't remember. So albite alteration basically dumps sodium into the rock. And in the fluid, the sodium had been charge balanced with the chlorine. And so to maintain that charge balance, you need to pick up a bunch of other elements. So that is usually calcium and potassium, but it can also be things like um, iron and copper and gold and that sort of thing. So those are iron and copper are usually mobilized around as chloride complexes in the crust, and gold can be if the fluids are oxidized enough. So when we look across these regions, we see that large volumes of these scapolite-rich rocks have been albitized. So that basically gets lots of chlorine into the fluid, and you'll also get uptake of calcium and potassium. We see lots of calcium and potassium alteration in the ore deposits where you eventually find the copper and gold. And so another consequences of picking up this calcium here as you go through albitization is that the two-phase field expands with the increasing calcium. So this is the two-phase field boundary for sodium. This is the two-phase field boundary for calcium. So the effect of driving albite alteration is to increase the phase separation. So it enhances the whole process, expands the solvus, enhances phase separation, increases salinity, increases the activity of water, drives more silica dissolution. So it's a enhancing process by going through this, enhances the metallogenic potential again. Coming back to this diagram now, we were talking before about normal orogenic fluids being down here. These ones are up here when you have sylviolite is the sulfate end member of scapolite. When you have sulfate in the scapolite coexisting with sulfides, you're much more oxidized. When you look across these regions, all of the copper gold deposits are really oxidized. And so the metamorphic fluids are the right sort of oxidation state, the right sort of conditions to be mobilizing all the iron we see in these deposits, and the calcium and the potassium and the sodium and all the copper and gold as well. Um, these ones are looking at the copper solubility as a function of some of these things. So increase the chlorine content, the copper solubility goes up a lot. Um, MPP is the magnetite pyrite pyrrhotite, HMP is the hematite magnetite uh, pyrite. And so under more oxidized conditions, you might get more copper in there. Under hotter conditions, you'll get more copper in there. Um, this one's for gold. And so this is kind of like a reminder that the maximum solubility is kind of on the sulfate sulfide fence, which is what scapolite buffers the crust to. So scapolite is buffering the crust to the ideal conditions for gold dissolution and great conditions for copper dissolution. So this is kind of what we think is going on in the Isa region. You'll have some regions where you've just got normal metamorphism going on during deformation. You'll get chlorine-rich fluids being liberated out of these scapolitic rocks, and you can probably form some purely metamorphogenic copper-gold systems. Other areas you've got intrusions going through into the same sort of rocks, and that heating and perhaps fluid liberation will drive breakdown of scapolite and the other chlorine-bearing minerals as well and form copper deposits there. So you can have sort of intrusion-driven systems and purely metamorphogenic systems as well. So you should expect to see both in some regions. So I'm kind of agnostic on whether you need to be purely metamorphogenic or it can be intrusion related as well. And so when we look across this region, we can see this sodium potassium alteration has progressed over 250 million years or whatever that adds up to. And you see mineral deposits that one of the ones we've been looking at recently is Mary Kathleen, which is the uranium rare earth element deposit. That one's formed over, several tens of millions of years. And many of the deposits look like they've formed over a long period of time. And so one of the characteristic things about these calc-silicate rocks is that they can continuously produce fluids, whereas they're a little bit different to the other metamorphic sources we talked about before. And over those sorts of time periods, you're probably talking about multiple stages of plate tectonics, multiple stages of orogenesis. So you can have reactivation of your metamorphic belt continuously producing ore deposits. And that's one of the ways that the Mt Isa Inlier is different to the other metamorphic belts we've been talking about. So it's kind of interesting. And getting sort of back to our oxidation state stuff, this is talking about oxidized conditions being good for transporting gold chloride complexes and copper chloride complexes and gold chloride complexes. And if you're able to reduce those oxidized fluids, you'll tend to precipitate out gold and chalcopyrite. And so one way you can do that is by magnetite precipitation. You're basically taking iron 2 plus out of the fluid and precipitating some iron 3 plus. That'll cause reduction of the fluid, which would decrease gold and copper solubility. So there's it kind of makes sense a lot with everything being transported around as a chloride complex. I'm trying to finish this off now, Jess, so don't worry too much. When we look at these sorts of fluids passing through the edges of some of these intrusions in the area, they tend to be quite rich in things like rare earth elements, uranium, that sort of thing. We tend to see a halo of uranium occurrences that tend to be enriched in rare earth elements as well around some of these intrusions. And we suggested a while back, this is a geology paper we had in 2016, that some of these really saline fluids were moving through the edges of some of these granites, and the chlorine-rich fluids were stripping out some of the uranium and the rare earths and mobilizing them along faults to form some of these ore systems. So these are orogenic uranium rare earth element deposits formed by these sorts of fluids. This is kind of like a summary of that general idea. This is some of the pictures of the weirdo minerals. So we had zircons and phosphates, and we were breaking down. The uranium was being mobilized as these were breaking down during as the really radiometrically hot fluids were as the radiometrically hot granites were basically becoming metamiced. So these sorts of situations here are great for later fluids to come along and pick up some of these elements and move them around. So we're basically the point here is that these during albitization, the brines picked up some of these elements. They picked up fluorine and phosphorus as well, and mobilized uranium earth elements, zirconium, to form some of the ore deposits were nearby. Um, with some of these multiple possible ligands being involved in this sort of process. So as a conclusion slide, we've got a comparison. So typical orogenic belts that form normal gold deposits we're used to thinking about. The fluids are normally produced by breakdown of chlorite in metasediments and mafic rocks, whereas in orogenic belts with meta-evaporites in them, so normal calc-silicates that are probably formed in an evaporitic setting. We still have peelites and mafic rocks in those regions as well, but we also have calc-silicates, and they're all fluid sources. So you get quite a heterogeneous variety of fluid chemistries being produced. In these orogenic ones, we get H2O rich, low CO2, low salinity, reduced neutral pH fluids like we know form orogenic gold systems. These ones, you get chlorine rich fluids, ligand rich fluids, which are really quite different to our other to these systems here. In graphite-free calc-silicates, the fluid FO, the oxygen fugacity is really quite oxidized, and it's really good for carrying metals as chloride and sulfide complexes at the same time. So you can get coal, gold and copper and iron and cobalt and all sorts of stuff mobilized by that sort of process. So the albitization enhances phase separation. You should get quite deep phase separation of the crust to separate the CO2 out, and have a quite efficient metal scavenging along those fluid channelways. And these are normal orogenic ones. You haven't got much in the way of ligands around, so you tend to get, apart from sulfur, so you tend to get gold-only deposits that are structurally controlled, whereas in the meta-evaporite rich belts like Mt Isa and Adelaide Fold Belt and some other regions in the world, you get a huge variety of different ore types, typically quartz poor, so you don't tend to see much in the way of quartz veins in a lot of these systems. So they're quite different to each other, but they're all forming in the metamorphic belts that reach the same sort of pressure temperature conditions. And I'll leave it there.
That was awesome. Thank you so much, Andy.